In this video, we study about rational expressions. We discuss these 5 topics: domain of an algebraic expression, and simplifying rational expressions, add, subtract, multiply, and divide rational expressions, and simplifying complex fractions and simplifying different quotients. So let's start with the first one. In this, we discuss a domain of an algebraic expressions. So before we talk about algebraic expressions, let's talk about the 4 different types. So we can start with the first we define what we mean by a function, what we mean by a domain. So a domain of an algebraic expression, so in this case a function, can be written as x such that fx is defined. So we're going to find all the values for which the function or the expression is defined. And then you can see that what we get is a set. So this is a set. This is a set. So that means we can use a set notation most of the time. So let's look at a simple example. So let's say we have, so let fx equal 3x minus 1 divided by x squared plus 1. And if you look at this expression, so you can think of what values you can plug in, and you can see that the denominator never becomes 0 because x squared plus 1. So you can see that this never equals to 0. So that means actually in this case numerator does not create any restrictions. So that means you can plug in any value for these functions. That means the domain is all real numbers. So domain, we can use the curly D. So domain of f is what we can say is set of all real numbers. So set of all real numbers. So set of all real numbers. So that's the domain. Since, you can say since, this is the argument, since x can be any real number, since x can be any real number. Because you can see that there are no division by zeros. So no division by 0, because that's what we kind of worry about. No division by 0. That's one thing we worry about. There's another one when we talk about root. Okay, so let's try to, so this is how we kind of like, look at a problem. You can see that it's not that difficult. It's a very simple idea. So let's look at those 4 different types one by one. So we're going to start with the first type. That's what we call the polynomial. So the first type, which are polynomials. So polynomials are the most innocent functions in mathematics. So they behave very well. So let's talk about that first. So what is a polynomial? Let's say I'm going to say px. So polynomial means just a number and x to an integer power, like positive integer power. And then there's another number x. You subtract the 1 by the power. So you start with a positive integer power and then you subtract every time 1. And then so it goes like that, and then you end up with cx plus d. So we assume that n is a positive integer or 0. So that's an assumption. So we assume that n is a positive integer or 0. N is a positive integer or 0. If it is 0, you just get a constant. But that's a special case. So, and you can see that there are no, because n is a positive integer, so that means there are no divisions now. There are no divisions and there are no roots. There are no square roots because n has to be a fraction in this case. So there are no roots, there are no divisions. That means you can plug in any value here. So that means if you have a polynomial, domain is all real numbers because there are no divisions or roots. So that means domain of a polynomial Domain of a polynomial is simply a set of all real numbers. The set of all real numbers. So this sometimes we write as curly r. So this is another notation. We write actually script r. We normally call this script r. So we write a script r for set of all real numbers. This is simply negative infinity all the way up to positive infinity. Also, if you graph this, this is all real numbers. So that means you're gonna draw a line, and then it is going from negative infinity to all the way to positive infinity. So the set is everything. So that means it is everything in between. So you can highlight it like that. So these are the three ways, actually four ways, to write the solution for polynomials. So a set of all real numbers, script r, or negative infinity to infinity, or just draw the whole line. That's the first type. So let's look at the second type. So second type is we can talk about the radicals. Radicals have two types. So so the second one, or part B, we can say radical. So radicals. Radicals are two types. So I'm going to call first type the type 1 radical. So type 1 radical. So you cannot find this specification in books. So this is something I discussed because it's much easier to do it this way. Type 1 radical. What are the type 1 radical? Like for example, y equal square root, not the square root, root n, y equal a root n, but we assume that n is a positive integer. N is a odd positive integer, is a odd positive integer. Odd positive integer. Odd positive integer. So when you have odd positive integers, like for example, like things like 1 and then 3, 5, 7, like that. Those are the odd positive integers. So so in this case, we can see that x can be anything. 0, negative, positive. So for all the numbers, this is valid. For example, cube root. If you look at the cube root, you can take cube root of any number, positive, 0, or negative. So that means in this case, x can be all real numbers. So this one is defined. This observation, you can see that this is defined for all real numbers. For all real numbers. That means the domain for type 1 radicals, the domain of type 1 radical is all real numbers. So script r. So that means the easy way to think about it, this is like polynomials. That's how you can think. It's like polynomials. Like polynomials. There are no problems. You can plug in anything. Good. For all real numbers. So let's look at the second type. This is what we call the type 2 radical. So type 2 radical. So what's a type 2 radical? It's y equal x root n. Here n is an even positive integer. N is an even positive integer. Earlier it was an odd positive integer, now it's an even positive integer. That's the difference. Even positive integer, earlier it was an odd positive integer. So for example, so the numbers can be 2, 4, 6, 8, things like that. But these you have to be careful because you can see that these, like for example, think of square root. So if you think that means n equal 2 means the square root. So so you can see n equal 2 means the square root. So we have x square root. This n equal 2. We don't write 2. It's the square root. So you can see that when it's a square root function, it's only defined for either 0 or positive. So that means the domain is restricted now. You can plug in a negative value for this one. So that means, so if you write a few examples like this, so we can say y equals square root x, or y equal sixth root, like this. So like even like in large roots, like let's say x going to 10 or 12, like that. Okay, so those are the type 2 radicals. In this case, domain is restricted, is only the values are greater than or equal to 0. X has to be greater than or equal to 0. So we can have the domain. So domain of type 2 radical is so x such that x greater than or equal 0. So if you use the interval notation, this also you can write as 0 to infinity. And then if you draw the line, so what happened? So it is it can start with 0 and then go to the right. So start with 0 and go to the right. So that's the domain. So this is 0. So those are the the 3 ways to write the domain for type 2 radicals. So let's talk about the next one, the rational expressions. So let's see the rational expressions. And we normally call the rational function. Rational function. So what's a rational function? So when you have the ratio between two polynomials, so if you write Rx, which is a ratio between two polynomials. So the ratio between those are two polynomials. So you call this a rational function. It's called a rational function. So for example, these are rational functions, like 1 over x is a rational function. 3x minus 1 over x squared minus 1 is a rational function. Maybe 2x over x to the fourth plus 3 is a rational function. So those are rational functions. So what you need to worry about in these cases, we need to look at the domain, because we need to avoid the division by 0. So that means if it's a rational expression or rational function, so the domain of a rational function, so like that, is simply you can avoid the values that makes the denominator 0. So you remove the values that makes the denominator 0. So we do not need to worry about the numerator. So just the denominator. You remove all the values that makes the denominator 0. And then we have a special case. Sometimes what happens, those px or qx may not be polynomial. It can be something else. It can be some root functions. So in that case, we call those are fractional expressions. So we're going to say quotient of two algebraic expressions, quotient of two algebraic expressions, quotients of two algebraic expressions, like with some like roots and some kind of other functions. So quotient of two algebraic expressions is a fractional expression, just a new name, fractional expression. So we don't necessarily say polynomials, or we don't say rational functions. We say fractional expressions. So for example, something like this. So let's say we have x plus 1 square root divided by x squared minus 2. So that's a fractional expression. So not polynomials. Or like 1 over x plus 3 squared. So those are what we call rational expressions. Not the rational expressions, the fractional expressions. So now when you want to find the domain, you have to think about all those different cases. So so we can think about all the other 3 types in this case. So the domain is the intersection So domain is the intersection of those three types, the other types that we discussed are those three types. There are three types. It can be a rational expression, or it can be a type 1 or type 2 radicals. Okay, so let's look at some examples to make sure that we understand the topics. So we will start with this example first. So let's say find the domain of each expression. Find the domain of each expression. So we can start with the first one. Let's say we have 4x3 minus x plus 3. So that's the expression we have. And you can see that this is a polynomial. So that means we can plug in anything for this one. So you can say this is a polynomial. So that's the argument. This is a polynomial. This is a polynomial. So a special word here. So the domain is all real numbers. So the domain is all real numbers. All real numbers. All real numbers. Let's look at the next one. Part B. How about 2x plus 3 square root? So you can see that this is a type 2 radical. So this is a type 2 radical. Type 2 radical. So you'll be careful with this one. So the condition is whatever you plug in here has to be greater than or equal to 0. That's the only condition. So 2x plus 3 has to be greater than or equal to 0. So that's the only condition. Now what we're going to do, we're going to simply solve this one. So this is not that difficult to solve. So we're going to start with 2x plus 3. So we solve this like the way we are solving an equation, but you have to be careful when you divide. So the first thing to do is move the plus 3 to the other side. That means you subtract 3 from both sides. So we can write this one as 2x. If you subtract 3 from both sides, it's going to be negative 3. Next, what we can do, we can isolate x, so we can divide by 2. If we divide by 2, x greater than or equal negative 3 over 2. So this says the condition. So it says that x has to be, it should be bigger or equal to negative 3 over 2. So domain equal x such that we can just copy this result here. So that's one way to write it. Just copy the condition here. Oh, this is actually equal to this, like another solution. We don't write all of them. So like sometimes we write the first version. That's what we normally call the set builder notation, or sometimes we go with the inequalities. We go with the interval notation. So this interval notation. So we put the number, and this is x is bigger. Then we go to the larger side. As I go to infinity. Also, we can graph this solution. So that's the interval. This is a bigger. That means bigger means right. Smaller means left. So we're gonna start with the value. So this is the negative 3/2 and go to the large side. That means to the right. Okay, that's infinity. So that is the graphical version. So that's how we write the solution for this problem. So let's look at the next one. C. So let's say we have 1 minus 5x to the cube root. And you can see that this is a type 1 radical. So this is a type 1 radical. Type 1 radical means they behave like a polynomial. So that means the domain is all real numbers. So the domain is the set of all real numbers. The set of all real numbers. Good. Um, so let's look at so set of all real numbers. So part D, let's look at a rational function. So let's say we have x squared minus 4 divided by x squared minus x minus 2. So this is a rational function. This is not a fractional expression, because you see those are both are polynomials. You can see these are polynomials. So this is a what we normally call the rational function. So when you have rational function, the theory says that we only need to worry about the denominator, just the denominator. So we are not going to factor or anything. Just look at the denominator, and you're going to make sure that you can avoid dividing by 0. That means we're going to remove the zeros from the denominator. That's the only thing we do. So that means the domain is simply x such that whatever the values that makes the denominator 0, we're going to remove them. So I'm going to make sure that the denominator is not equal to 0. So the not equal sign is the important one here. And we only pick the function from the denominator. So now what we do, normally we actually set this equal to 0 and figure out what values that makes this one 0, and we can remove them. So we can do it here. So we say, okay, so we're going to set this equal to 0. So we're going to find all the fault values. To do that, we're going to factor this. So we're going to factor this. This is easy to factor. This is x minus 2 and x plus 1. Those are the two factors. Now we're going to set each factor equal to 0. Or x plus 1 equal to 0. So this says x equal to 2. And then this says if you subtract 1, x equal negative 1. So those are the two values that makes the denominator 0. That means we're going to say x such that x not equal to 0 and because both can be, and x not equal, and then x not equal to negative 1. So those are the two values that we need to remove. So that's one way to write the solution. The other way to write the solution, we can use the interval notation. So if you use the interval notation, what's going to happen, you can write this one as, so we have to remove two values. So how to remove two values? We start with negative infinity, and then stop at the first value, which is negative 1, and then like a open, that means open, and then put a union, and then start at negative 1 again and go to the next larger value, in this case 2, and open it again, and then put the union, and then start at 2 again and go to infinity. And you can see that when you write it, this what we do is we remove the here we remove the negative 1, here we remove the 2. So that's how you remove two values or any number of values, but since we have 2, we did it like that. So, and if you look at the graphical notation, and you can see it's very similar after we have this first version. So we're gonna first remove the values. So we're gonna say open dot at negative 1 and then open dot at 2. So this is negative 1 and 2. Now we can highlight the rest. So that means, so this is one part, and we highlight in between. Also we highlight after. And then you can see this is negative infinity, this is infinity. So this is the graphical version of that. So you can write any of these versions unless the specific one is requested in the exam. Okay, let's look at the next example. So next we have, this is E, we have 1 minus 3t square root divided by, let's say, t squared plus 4t plus 4. And then you can see that because the square root sign, this is not a rational function. This is because there's not the top is not a polynomial. So this is what we call the fractional expression. Fractional expression. So what we're gonna do, we're gonna consider the cases we considered earlier. For example, we can look at the numerator and denominator separately. So from the numerator, that means the top, from the numerator what we get, so we can see that this is a type 2 radical. So this is a type 2 radical, and we know how to solve type 2 radicals. We're gonna look at what is inside, and we're going to impose the condition that the inside function has to be greater than or equal to 0 because this is square root. And then this is very easy to solve. So we can see we're gonna leave 3t on this side and remove 1, so they subtract 1 from both sides. Now you have to be very careful. We have to divide by negative number. So when you divide by a negative number, what will happen? You're gonna switch the direction of the inequality. If you divide by negative 3, it's going to be t. You can switch the order. It's going to be negative 1 over negative 3. So right after you divide, switch the direction of the inequality. Now this you can simplify. This is just 1/3. So that means, so what this says that t is less than or equal 1/3. So this is one way to solve this problem. Let's discuss another way to solve this problem. The other way to do this is you can actually, so we can start with 1 minus 3t greater than or equal to 0. So the next step is we're going to move this term to the other side. So do that, we add 3t to both sides. So that's another way to do it. So we add 3t to both sides. The easiest way to think about it, if you move a term from one side to the other side, is switch the sign. That's it. That's the easiest way to remember this one. You can switch the sign. It doesn't matter what side to what side. Switch the sign. Now we can divide by 3. Since it's a positive number, so you can see that just 1/3 greater than or equal t. So in other words, it says that t is smaller than 1/3. So we can once we get this, and we can completely turn the equation. So what we do, we can write this one exact same one, t less than or equal 1/3. So we can write it like that anytime. You can switch the whole equation around. So remember this one as a shortcut. Like if you have an inequality or equation, you can always turn the whole equation around, but make sure it's also switch because the small side is towards t. So it should be like that. And you can see that the smaller side is towards t. Again, it should be the same way. So this is the other way to solve the problem. So you can solve it in either way. Okay, good. So that's the first condition. So what's the second condition say? What's the domain says? So if you look at the domain says that the t squared plus 4t plus 4 not equal to 0. That's what it says. And then as before, we're going to find the factors. And this case, this is very easy to factor. So this is a complete square. So we're going to get like that. And it's not equal to 0. And then if you take the square root, you can see that t plus 2 not equal to 0. In other words, this is that t not equal to negative 2. So that is the number you have to remove. So that means now we can write the solution, because the one says that t has to be less than or equal 1/3, and this one says t cannot be equal to negative 2. So we're going to put, because it has to have both conditions. There's an and involved here, because both means and. Both means and. So we're going to convert in mathematics, the both, we can convert it to and. So let's try the solution now. So we can say, so thus, the t has to be less than or equal 1/3 and t not equal to negative 2. So the domain equal t such that t not less than or equal 1/3 and we satisfy both, and t not equal to negative 2. So that's how we write it. You have to write and there. It's not a o, it's and. We satisfy both conditions, and means both. So and then if you graph it, it's going to be very simple. So it's a line, and negative 2 is removed. That's negative 2. So we can start with 1/3, that's on this side. So it will be everything below that, but without negative 2. So that means there's a solution. So you can go there and go there. That's a solution. And this is the 1/3 here. That's how we write the solution. And then also, if you write the interval notation, you can write it like this: negative infinity, negative 2, and then union we have -2 1/3. So that's the 1/3 actually is including 1/3, so we can include 1/3 there. So that's the solution. And then you can try these problems as practice problems. So you can also do if the sixth one. There are two expressions, so you want to think about how to combine this. So there's an AND condition coming here.